Before we can begin working with probabilities of binomial experiments, we need to make sure we understand what a binomial experiment actually looks like. All binomial experiments have 4 characteristics that must be true. So first one is a set number of trials, meaning we are going to perform a certain trial multiple times, and you're going to decide how many times you're going to do that trial at the beginning of your problem, and that is not allowed to change. So if you decide I'm going to flip this coin 20 times, then you're only allowed to go 20 times. You can't go 19, you can't go 21. It has to be 20 times. That number is not allowed to change. Next, what do we have? Trials are independent of each other, meaning the outcome of one trial does not affect the outcome of another trial. We also have that each trial has exactly 2 outcomes, which we will call a success and a failure. And then the fourth is that the probability of success is the same for each one of these trials. So the probability of getting a success does not change from one trial to the next. In order to be a binomial experiment, we have to meet all 4 of these conditions. If we're checking to see if something is a binomial experiment and it fails the very first one, then we don't need to bother checking the other 4. You can just stop right there and say, nope, it's not a binomial experiment. So we have to meet all 4 of these conditions. So we're just going to look at a few different examples to quickly determine whether something is or is not a binomial experiment. So number 1 says we want to flip a coin 10 times and count the number of heads that come up in each trial. So first one, do we have a set number of trials in this case? Yes, we do. We're flipping it 10 times. We usually use the variable n to represent the number of trials. So if you want to make a note here, we can even say n is the number of trials, which in this case is 10. We know exactly how many times we're going to flip this coin. 2, what do we have here? Trials are independent. Well, if we're flipping a coin, each coin flip is going to be independent. The coin doesn't remember whether it came up heads or tails last time. Each one has a 50% chance of coming up heads or tails. So in this case, yep, that seems to work. Number 3, exactly 2 outcomes. Well, in this case of a coin flip, yep, there's only 2 outcomes. It's either heads or it's tails. So yes, we do meet that one. And then the 4th, the probability of success is the same for each trial. We should be able to find that probability of success. In this case, because there's only 2 outcomes, heads and tails, each outcome is equally likely. That means the probability of success, which we often call P, is 1/2 or just 0.5. So as we're checking these, we should be able to tell 2 things. We should be able to tell what is n, the number of trials that we're running, and then what is p, the probability of success. And if all of these conditions are met, then yes, this is a binomial experiment. So we could use our binomial probability formulas that we're going to talk about later on in this section to answer questions about this particular experiment. Let's take a look at a couple more here. Number 2 says flip coins and count the number of flips until a total of heads comes up. So if I wanted to go through this and talk about each one of these conditions, the first one, how many trials are we running? Well, it kind of depends. We're going to flip coins and count the number of flips. I don't know what n is. It just depends on, maybe we get lucky and we get 10 in a row. Maybe it takes us 20. Maybe it takes us 30. I don't know. And if we don't have a clear value for n, this is not a binomial experiment. So it fails the first condition, which means I don't even need to check the other outcomes. I can just say, nope, this is not a binomial experiment. I don't need to check conditions 2, 3, or 4. I can just stop right there and say, no, we can move on. This is not a binomial experiment. Continuing on, number 3 says deal 5 hands of cards from a single deck. Count the number of kings in each hand. So in this case, let's think about this. First of all, do we have a set number of trials? It sure seems like it. We've got 5 hands of cards, so I would assume that n is equal to 5. Number 2, our second condition is that trials are independent of each other. So if one hand has 4 kings, is that going to affect the other hands of cards? Well, in this case, yes, it would. I'm assuming I'm drawing these hands without replacement, meaning I'm going to kind of deal all of these hands at the same time and count the number of kings. So in this case, if they're dealt without replacement at the same time, then that means that these are not independent. And if our trials are not independent, that means that this is not a binomial experiment. Now, I should say it's a little bit perhaps unclear about this question, whether we're dealing with replacement or without replacement. If I was going to deal one hand, look at the number of heads, or excuse me, the number of kings, shuffle it back in and do this with replacement, this would actually be a binomial experiment, but I'm going to assume that this is without replacements. If this was with replacement, then in that case, it would actually be a binomial experiment. But without replacement, it will not be a binomial experiment. Looking at our last example down here, it says, suppose that it is estimated that 85% of students love math. We randomly select 200 students and ask, do you love math, yes or no? Count the number of students who answer yes. So again, in this case, we should be able to check all of our conditions, starting with the number of trials that we're running. How many students are we going to talk to? In this case, we're talking to 200 students. So we are randomly sampling 200 students. Next one, independence. This one's perhaps a little bit tricky. I'm assuming I'm going to pull from a large population, and in situations like this, if you're working with a very large population, it's pretty safe to assume that the students that we select are independent of one another. So we can go ahead and assume that these are going to be independent in this case. Number 3, we said exactly 2 outcomes. In this case, we're asking either yes or no. So yes or no. So yeah, sure, this has exactly 2 outcomes. So there certainly seems to be exactly 2. And then for our 4th case over here, we're defining a success as the number of students who answer yes. So the probability of selecting a student who answers yes, it seems like is roughly 85% if we're selecting randomly. So my probability of success for each one of these trials, each one of these students, is 0.85. So yes, this condition is met. So we've met all 4 of our conditions. So in this case, yes, this is a binomial experiment. So as you're working through some of these problems, try and make a mental note about these 4 conditions. Think about, how many trials am I running? Are my trials independent? Are there 2 outcomes? And is the probability same for each one of these trials?